So today we'll be continuing our study of vectors, and specifically we'll be looking at the nitty-gritty of the magnitude and the direction of vectors. So if we look at the magnitude of a position vector, that's the easiest kind of vector to work with, because as you know from our last lesson, position vectors are vectors that start at the origin and then go to a point from there. So we can just use Pythagoras' theorem when working with these sorts of position vectors to really just get an idea of their length. Because they start at the origin, we can separate them into an x component and a y component, and that's given by our x and y points. And then from there, we can essentially just treat this like a triangle in Pythagoras' theorem, and then just use a squared plus b squared equals to c squared, where our a is our x and our b is our y, so we get y squared, and our length, or our magnitude, so our u with an absolute value brackets around it, is squared. So that's where we get this expression from. So our c is our magnitude, which is the diagonal. And we've got our x and our y components. And then if we just rearrange this, we get u equals to square root x squared plus y squared. So that's where this comes from. It's essentially just Pythagoras' theorem. You should be able to do this. It's nothing too major. So when you see a position vector and you see the absolute value signs, it just means you use Pythagoras' theorem on the points, the x and the y points. So now looking at an example of that, then we have to find the magnitude of -3, 4. And this is a really common example because this is actually a really nice value. So before I go into the magnitude, just looking at what this example is, then we have -3 in the x direction. So we have our x and our y directions. And we have -3 in the x direction, and we go up 4. So we're actually going to be here. So we end up with, let's just do those different colors. We actually end up with this triangle here when we have a vector pointing that way. And that will be 4 long, and that will go across -3, so that'll be 3 long. So what we're going to do now is set the absolute value of v, i.e. the magnitude. So the magnitude of v is going to be square root bracket -3 squared plus, sorry, that should be there, plus 4 squared, using that formula from before. Then we're going to find from here, this is the square root of -3 squared is 9. 9 plus and 4 squared is 16. So 9 plus 16. And so that's going to give us square root of 25, which is just equal to 5. So that means that the magnitude of this vector v, meaning its length, is going to be 5. And that's it. And so that's relatively simple, and that's how you find the magnitude of a position vector. So now looking at an example of when we don't necessarily have a position vector. So in this case, it's a displacement or relative vector, which is essentially any vector that doesn't start at the origin. It starts at some other point and then it continues from there. So this is just a little bit different, though it should look familiar. And again, it's just Pythagoras' theorem, except instead of just having a distance of our x value and our y value, we've now got the difference between our two x values and our y values. I know that these 2 points, OX and OY, they are position vectors. So there's 2 position vectors. This is our OX, because we're going from the origin to our x, and this is our OY, because that's going from the origin to our y vector. And the reason we're using these 2 points is because these 2 position vectors just describe the points at the end of those vectors. So essentially, it just defines this point for our OX and this point for our OY. And from there, it's just the distance between 2 points. And if you remember any coordinate geometry, you'll know that this is just the formula for the distance between 2 points. And that's essentially what we're doing. Our vectors OX and OY just define 2 points here and here. and then we're just finding the distance between them because that gives us the magnitude of that vector. And because this is a relative vector, we need the 2 points because we're not starting at the origin. So now looking at an example, it might clear a few things up. So if we're looking at this now, we want to find the exact magnitude of AB, where OA is equal to 1 on 1, 2. So x1, y2, and OB is equal to 3 minus 2, so x is equal to 3, y is equal to minus 2. So if we just draw that up really quick, then what we're looking for is a vector going from 0 to 1, 2. So this is our OA vector, so that's point A, and then OB is 3 minus 2. So we'll have another vector going down here to B. So then the vector that we're finding the magnitude of, our AB, is going to go from A to B. And so we want to find the magnitude of this blue vector here. And so the way we're going to do that is we're going to take point A, which is 1, 2, and we're going to take point B, which is 3 minus 2, and we're just going to find the distance between those 2 points, just like you would in normal coordinate geometry. And so that's going to be that the magnitude of AB, the vector, is equal to the square root, and it's going to be the difference between the two x values and the difference between the two y values. So earlier in the formula, we had one point that was x1, y1, and we had another point that was x2, y2. Now, importantly, when you're doing this formula, it doesn't matter which one you actually put first, whether it's x1 or x2, because it doesn't matter which way we really define them. We're going to get the same distance between them, but it is really important to stay consistent. So if this becomes your first point, so let's say that this is point 1, so that means that's x1 and this is y1, then we can't then interchange between the two. That means this has to be x1. If this is x1, this has to be y1. It can't be y2. And if this is x2, this can't be y1. This has to be y2 as well. So this has to be then our second point. But it doesn't matter which one is first and which one is second, because it doesn't actually affect the equation. So we end up with x2 minus x1 squared plus x1, sorry, not x, that should be y, y2 minus y1 all squared, and then substituting in here. So then our x2, we go to point 2 and we go to the x, so that's 3. So that's going to be 3 minus, and we go to the first point and we go to the x, which is 1, minus 1 squared plus, and we go to y2. So we go to the second point, the y, which is minus 2, and then y1. We go to the first point, you go to the y, that's 2, and then we square that. So what we end up with is 2 squared plus minus 4 all squared. So then that's going to be 4 plus 16. So that's going to be equal to the square root of 20. And now we can simplify that to be 2 root 5. And that's just using surds. So that means, just put it over here. So our solution is that the magnitude of AB is equal to 2 root 5. And that's a very common format because when we're dealing with these sorts of square roots, it's actually really rare for you to actually get a perfect square because there's a lot more numbers that aren't perfect squares. So you're very likely to get a surd involved. So don't be too afraid if you do get a surd. That's pretty normal. All right. So moving on, what happens when we want the direction of a position vector? Well, if we think back to the gradient formula, it gives you the direction essentially. And a gradient is considered your rise over your run. So in this case, it's your rise over your run. So then if we look at that in terms of tan, which is opposite over adjacent, and from this triangle, this is opposite and this is adjacent, then we can look at this formula here to define our direction. So this is actually equal to our gradient as well, because this is rise and run. So we end up getting the same thing. It'll be our rise over our run, or if we're looking in terms of tan, our opposite over our adjacent. And so from here, we can then rearrange this to be theta is equal to tan inverse y over x, and that will give you the angle it's pointing at with respect to the positive x-axis. So note, if you get something that is not within the first quadrant, then that means it might be pointing over here, or it might be pointing down here, or it might even just be pointing there. So we're going to be using this formula quite a bit in general practice, but I'll show you an example later. And it is essentially really useful at getting the angle or the direction of your vector. And in this case, it's really useful for the position vector. And again, I'll go into the relative vector after this. Anyway, looking at an example, if we want to find the direction to the nearest degree of OA, well, the formula is tan theta is equal to y1, sorry, not y1, just y over x. And so in this case, our y value is 3, and our x value is 5. So it's going to be 3 over 5 from our y over x. And then we can rearrange this. So we get theta is equal to tan inverse 3 over 5. And then if we just put that into the calculator, we should get about, it's going to be approximately, and once the nearest degree is going to be approximately 31 degrees. And feel free to double check that. And if you look at the signs, this is positive and this is positive, which means it's going to be in the first quadrant. And that should be correct because we've got a 31 degree angle. So if it wasn't in the first quadrant, you might have to look at what the angle is going to be with respect to the positive x-axis. And so if we look here, our vector is going to be going this way, and it's going to be 31 degrees. And so that's the direction our vector should be going in. Anyway, looking at relative coordinates now, or relative vectors now, or displacement vectors, this is looking much more like a different gradient formula now. And this is actually the regular formula that we use for gradient, which is the rise over the run. Again, and again, just like with the magnitude example, it's going to be the difference in the y's and the difference in the x's, and that's going to be giving us our two sides of this triangle. And from there, it's just the same mass in that this is going to be our opposite, and this is going to be our adjacent. But now we have to find the difference between the 2 points because we have two position vectors that define 2 points at the end of our vector, and we want to make a triangle between those 2 points. So it's just the exact same mass, except now we just introduce the same point, the 2-point system, and we just substitute into this formula. You should know how to use this formula from your previous studies. Just make sure you use it with the position vectors and not any other vectors. So looking at an example of that, we want to find the direction of AB to the nearest degree, where OA is equal to 1 over 3 and OB is equal to -2 minus 1. So what I'm going to do is I'm going to call this my first point and this my second point. And so the formula is tan theta is equal to y2 minus y1 all over x2 minus x1. And so from here, what we're going to get is that tan theta is equal to -2 minus 1. Sorry, I did that the wrong way around. That should actually, and it should be important to note, pay attention to which one's your x's and which one's your y. So we're starting with y's first, so we should start down here. So y2 is actually going to be the y coordinate of our second point. So that's going to be -1, and then our y coordinate of our first point, which is going to be 3. So -3 all over. And now we're looking at our x's. And so we get x2 is going to be -2. And x1 is going to be 1. So that's -1. So then what we get is minus 4 all over minus 3, which is just equal to 4 over 3. So then we can rearrange this to get theta is equal to tan inverse 4 over 3. And if we put that into our calculators, we should get something that is approximately, and I'll use the wiggly equal sign for approximately again, this is approximately going to be 53 degrees. So the angle is going to be about 53 degrees. Now, if we look at this though, if we look at the points we actually have, we're going from 1 up to 3, and this is where we're starting. So this is our point A, that's 1, 3, but then we're going to minus 2, minus 1. So this is our point B. So our vector is actually going to be pointing down into this direction. Now, when we have 53 degrees here, we would expect that this angle would be 53 degrees because this is the angle with respect to the positive x-axis. So we would expect the angle with the positive x-axis to be 53 degrees. That, however, is not the case because we have tan, and tan is positive in what two quadrants? It's positive in the first and the third quadrant. If you remember your all stations to central. So since we're getting a positive tan value, it's just going to give us the first quadrant angle. It's not actually going to give us the third quadrant angle. So we have to find the third quadrant angle now because that's the actual angle we want for our direction. Because if we look at our points, it's clearly not going 53 degrees with the x-axis. It's gone all the way around and is now pointing down and backwards. So the formula for third quadrant angles is we go 180 plus theta. Sorry, theta, not 30. So we go 180 plus theta, and that gives us our angle. And if you're unfamiliar with that, go back and look at some previous trig notes, but this is just basic work with the unit circle that you should have already learned in advanced mathematics. So from here, we have 180 degrees plus theta. So our theta here is 53 degrees. So that means our actual angle is approximately 233 degrees. So it's not the initial 53 degrees because if we look at the positive x-axis, it's going here. And the angle we want goes all the way around and points us in that direction there. And so that's where our 233 degrees comes from. So that's really important to note. And this isn't just the case for relative vectors. You also have to think about this with your position vectors. In the previous example, like I mentioned, it was in the first quadrant, so the 31 degrees works perfectly. But if it was actually in the third quadrant, meaning both its x and y values were negative, then what you would want to do realistically is to do this same process where you find the quadrant. And it also works if you get something in the second quadrant. You have to check that it's actually not an angle in the fourth quadrant. So just be mindful of your points, but you also have to find your angle. Anyway, I hope that lesson was helpful, and I hope to see you guys in the next one.